Okay, so take a look at this first example and see if you can figure out how to do it on your own. Before you get started, I want to give you a couple of hints, and that is that you want to make sure that all of your quantities are given to you in terms of SI units. Now, this 33 and 1/3 RPMs is omega, but it's using revolutions per minute instead of radians per second. So you're going to have to make a conversion there. Go ahead and give it a try, and then we'll see how you did. Okay, welcome back. So the first thing we're going to do is make a conversion of 33 and 1/3 RPMs to radians per second. Now, when reading the problem, this 33 and 1/3 RPMs is going to be omega final, and omega initial is going to be 0. So omega initial is 0, but omega final is 33 and 1/3 revolutions per minute. So let's do that conversion. So we have 33 and 1/3 revolutions in 1 minute, and then we're going to convert revolutions to radians, and we know that 1 revolution is going to be 2 pi radians. So we need revolutions to go on the bottom. It's 1 revolution, and we said that it was 2 pi radians. Then we need to convert the minutes to seconds, and so 1 minute is going to be equal to 60 seconds. All right, so whenever we go through our calculation here, what we're going to do is 33 1/3 times 2 pi divided by 60. And we get a value of 3.49 radians per second. So this is going to be 3.49 radians per second. So this is 3.49. Okay, so now what we need to do is we need to determine the number of revolutions required to reach that speed. So what we're looking for in this problem is the displacement, or delta theta. So this is what we're looking for. And they tell us that the time interval is going to be 3.2 seconds. So looking at our equations, the one that's probably going to do this the easiest is the one which does not include acceleration, because acceleration is an unknown quantity. And so what we get is delta theta is equal to 1/2 times omega initial plus omega final times t. So delta theta is equal to, now omega initial we said was 0. And this is just going to leave us with omega final times t divided by 2. And so that's going to be 3.49 times the 3.2 seconds divided by 2. So we have 3.49 times 3.2 seconds divided by 2. And that's going to give us 5.58 radians. Now, there's only one problem. This is in radians. The problem is asking for revolutions. So once again, we're going to have to do a conversion. And what's the conversion? Well, we have 5.58 radians, and we need to take that to revolutions, and we need radians to cancel, so that'll go on the bottom. So there is 2 pi radians in 1 revolution. So we take our answer of 5.58 and we divide that by 2 pi, and delta theta will become divide that by 2 divided by pi. 0.889 revolutions. So 0.889 revolutions. So that's the answer to part A. Now part B, we want to know what the angular acceleration is, and we're assuming that it's going to be a nice uniform and constant acceleration. So for part B, we're just going to use our velocity function or the definition of acceleration. We have omega final, we have omega initial, and we know the time interval. So we know from translation that A is equal to V final minus V initial over T. So if we put this in terms of our angular variables, we would say that alpha is equal to omega final minus omega initial divided by T. Omega initial was 0, and so omega final is 3.49. Divide that by the 3.2 seconds, and our acceleration becomes 1.09 radians per second squared. Okay, so let's take a look at another problem. Okay, so here's example number 2. Two children just playing at the playground. There's a merry-go-round, and it takes 1/2 of a rotation or 1/2 of a revolution to get the merry-go-round up to the maximum possible speed that it's going to reach. And the final speed is going to be 1 revolution for every 8.2 seconds. So take a minute, see if you can figure this out. This is a very unorthodox way of writing omega, but it is still omega. So let's see what you come up with. Okay, welcome back. So let's see how this goes. So omega initial is going to be 0, and omega final they give us in this really cryptic manner, which is 1 revolution every 8.2 seconds. Now, it's easy to figure out what omega is from this because omega final is going to be a constant omega if those children continue to just push that merry-go-round in a circle. Okay, so because it's a constant omega, then we can just use our definition for average angular velocity. And that is, well, you'll recognize it more from translation. So we would say that V is equal to D over T. And so in this case, we're going to say omega is equal to the angular displacement, which would be 1 revolution, divided by the time interval for 1 revolution, which is 8.2 seconds. Now, we don't want to leave this as revolutions, and since we know that it's supposed to be 1 revolution in 8.2 seconds, we can just write that as 2 pi radians every 8.2 seconds. And so all we have to do now is the math to get what omega final is. So that's 2 pi divided by 8.2. And that's going to be 0.766 radians per second. So we have 0.766 radians per second. All right, now we're looking for the angular acceleration, alpha. So this is what we want. And the time interval is unknown. And remember that delta theta, for our purposes, is going to be pi, because we complete 1/2 of a revolution in order to get up to this angular velocity. So which equation is going to work best? Think about that. All right, well, don't forget that if we don't know time, then it would make the most sense to start with the equation which does not include time, or omega final squared is equal to omega initial squared plus 2 alpha delta theta. Now this was the rotational equivalent of V final squared is equal to V initial squared plus 2AD. Okay, so let's simplify. We know that omega initial is 0, so that's going to go away. And now we just look for alpha, so we'll solve this equation for alpha. And what are we going to get? See here, omega final squared divided by 2 delta theta is equal to alpha. So omega final is 0.766 squared. Divide that by 2 times pi. So we have the 7.66. We're going to square that answer and divide it by 2. Divide again by pi. And so what we get is alpha is equal to 0.093 radians per second squared.